Essential question is, how can we use our knowledge of integrals to find the area between two curves? So imagine that we have two functions. Let's call this one f of x, and let's call this one g of x. And if I wanted to bound this area from, say, A to B and find the area between them, we can do this mathematically by integrating from A to B the top function minus the bottom function. So essentially, integral from left to right of top minus bottom dx. Now this works only for functions defined by x. There will be times where you might have a function defined by y. So let's say we have some sort of sideways parabola here, and we'll call this g of y. And let's also make some sort of linear function, and we'll call this one f of y. And instead of bounding it with x's, let's actually bound it with y values. And let's go from C to D, and let's say we're now interested in finding this area under the curve. Well, it's going to be the integral from C to D of f of y minus g of y dy. Now the order that you're putting these in does matter, because now we're going from bottom to top y bounds of right minus left dy, and this works for functions defined by y. Essential to all of this, though, is that the order that you write things in does matter. Okay? When we're talking about the representative rectangle, thinking about that Riemann sum, remember our slices on when we're doing a function defined by y are going to be oriented up and down. Our representative rectangle for our Riemann sum will actually be oriented side to side when we are doing a function defined by y. So let's go to an example. It is important that you know that you must be able to graph all of these examples without a calculator and construct the graphs. Now, do the graphs have to be perfect? No. Do you have to be able to make some sort of sketch? Absolutely. So I have a parabola, negative x squared plus 3, so a parabola that is opening down and that has been shifted up 3 units. So it's going to have a point at 0, 3, at negative 1, 2, at 1, 2, at 2, negative 1, and negative 2, negative 1. Now, if you're not very good at remembering your transformations, that's okay. You can plug in points and still get the exact same values that I have. And then we have a linear function, pretty simple, negative x plus 1. So it's going to have a y-intercept of 1 and a slope of negative 1. Hopefully you graphed that a little bit better than I did, and there we go. Now we're interested in the area bounded by these two graphs. When we say bounded, it must be completely restricted by the two functions. So we're going to use the area formula that goes from left to right of top minus bottom, because there are clear top and bottom functions in this case. But I have to know what those left and right bounds are. Now, if you can't find those left and right bounds graphically, remember that you can always find intersections by setting the points equal to each other. So if I set these two functions equal to each other, and get everything on one side, I have a positive x squared minus x minus 2, which does factor into x minus 2 and x plus 1, which aligns with our current graphed points of intersection of 2 and negative 1. That means my integral will go from negative 1 to 2. The top function is the parabola, so 3 minus x squared. The bottom function is the linear function, and we need a set of brackets to bound this with a dx. Now, I'm aware you could use your calculator to calculate this integral. We're going to do this by hand because it's good for the soul, and you're going to be expected to do this by hand on the AP exam. I would encourage you, though, to simplify what's in your integrand before moving on. So I'm going to do that. This will become 3 minus x squared plus x minus 1 once I distribute the negative. Combining my like terms, I have negative x squared plus x plus 2. Using my integral rules, I've got negative x to the third power over 3, x squared over 2, and 2x, and we're going to be evaluating the entire thing from negative 1 to 2. Be careful with your parentheses when you approach this because that's going to become pretty important. So let's start our substitution. Negative 2 to the third power, and that 2 is being cubed before it's being negative, 2 squared over 2 plus 2 times 2 minus negative 1 to the third power over 3, negative 1 squared over 2 plus 2 times negative 1. 2 cubed is 8, so that's going to give us negative 8 thirds. 2 squared is 4. 4 divided by 2 is 2, and then we've got a plus 4 right there. Negative 1 cubed will be negative, but then when I apply the other negative, that will become a positive 1 third, a positive 1 half, and a minus 2 right here. I've got negative 8 thirds plus 6. Let's distribute our negative sign. Negative 1 third, negative 1 half, and plus 2. I'd encourage you to always work with what you have that is a common denominator. So if I use the negative 8 thirds and the negative 1 thirds, that's going to be a negative 9 thirds, also known as negative 3. And then my 6 and my 2 will give me 8 minus a half. So I have 5 minus a half, which is 4 halves, or 4 and a half, which is 9 halves units squared, because this is an area, okay? But you will not always have the luxury to be able to do functions defined by x. And so now that we're in AP Calculus BC, it is highly plausible that you could see a function defined by y. Now, you guys are not used to graphing functions defined by y, so let's talk about how to approach something like this. Most of us would look at this and clearly know this is a parabola oriented sideways, but if it needs help and you're not sure how to graph it, solve for y. I'm going to get x minus 5 is equal to negative y squared. If I apply the negative, 5 minus x is equal to y squared, which means y is the positive and negative square root of 5 minus x. Well, that means that this is a parabola that's oriented sideways, or if you want to think about it as a square root function that has been shifted to the right 5 units, and it's going to be turned on its side. And if you want to find some more points, remember that you can always plug in. I think if you plug in 1, you'll end up with 1 and 2, and negative 1 and negative 2. Now that's kind of a wonky looking parabola. We're going to do better. Fake it till you make it. And I want to say if we plug in -4, we should end up with 3 and -3. Don't quote me on that. Always check. And then my other equation is x equals y minus 1. Add the 1 to this side and you get x plus 1 equals y. So that's just a y-intercept of 1 and a slope of 1. And there's our linear function. Now I want the area that's bounded between them. So we're talking about this area right here. And notice there's not a top and bottom function. There's a right and a left function. So when I say right and left, this is the rightmost function. This is the leftmost function. There's a right side and a left side to this area. So we're going to use the equation that area is from bottom to top of right minus left dy. And we're going to use them in their functions defined by y format. Now, we've already found these points of intersection and I can see them graphically, but if you didn't know how to find them, remember, I can set these two equations equal to each other and get y squared plus y minus 6, which factors into y plus 3 and y minus 2 to give us 2 points of intersection, y equals -3 and +2, which does check with our graph. So that tells me the bounds of my integrand are going to be from -3 to 2. My rightmost function is going to be the parabola, 5 minus y squared. My leftmost function is y minus 1. I want you to simplify this before you go taking integrals. So we're going to turn this into -y squared minus y plus 6. And again, for the good of our souls, we're going to do this by hand. -y cubed over 3 minus y squared over 2 plus 6y, the entire thing evaluated from -3 to 2. I'd like for you to go ahead and press pause and practice plugging in. I think that sometimes we tend to be a little bit rusty with fractions, so I want you to have that practice. So press pause and give it a go. All right, so let's see what we've got. -2 cubed over 3, 2 squared over 2, plus 6 times 2. Believe it or not, most of the mistakes come when you're actually doing the algebra piece of this. -3 cubed over 3, -3 squared over 2, 6 times -3. So cubing the 2, we'll get a -8/3. 4 divided by 2 will give us 2, and a 12 right here. -3 to the third power is -27, but then we'll make it positive. So 27 divided by 3 is 9, minus 9/2 minus 18. For a -8/3, plus 10, minus 9, plus 9/2, plus 18. Add up all of your numbers. So we're going to have a 19 minus 8/3 plus 9/2. Yes, I am expecting you to be able to find common denominators. So that's going to be 6. And when all is said and done, we have 114/6 minus 16/6 plus 27/6 for a grand total of 125/6 units squared. Okay, So I'm not always going to be so terribly mean that says that you absolutely have to do this by hand. You can do some by your calculator. In fact, you can even graph them in your calculator and find intersections, and that is one of the things that your AP exam is going to be expecting you to be able to do. So an x to the 6th is like a really flat parabola. Obviously, it has the points 0, 0, and 1, 1, and negative 1, 1. And then we have x plus 2, which has a slope of 1. And keep in mind, this is just a sketch. And so if I want to find the intersections, I can't show this because I don't have an emulator on my screen, but I'd like for you to graph these two, set them equal to each other, put this in y1, put this in y2, and I want you to find the 2 points of intersection because we're going to be needing those in order to construct this area. The first one I can actually see graphically, and you should see it on your calculator. We get x equals negative 1. But the second one, I'd like for you to tell me what it is. Okay, so coming back from your calculator, you should have got 1.2148623. Why did she hold out so many ridiculous decimal places? Well, the more decimal places you hold out, the more exact your answer is going to be. So it's important that you preserve those decimal places. Remind me in class to show you how to store this as a variable to make your lives a little bit easier without having to type in all those decimal places. So we're going to use the formula because I have a top and bottom area from left to right, top minus bottom dx. So we're going to go from negative 1 to 1.2148623. Why does it matter? It matters. Our topmost function is x plus 2. Our bottom function is x to the 6th dx. Now you're going to use your calculator for this, so I'd like for you to press pause again, go in your calculator, and tell me what you get. If you're joining us back, the integral you got from your calculator, 3 decimal places always, 3.967 units squared. If you did not get that answer, then you most likely have something that you didn't hold out enough decimal places. Okay? All right, so I want to bring a point to what's going to happen if you have 2 functions that cross places. So grab a highlighter, colored pencil, marker, something of that sort. And I want you to highlight the f of x function and grab a different color and highlight the g of x function. And you notice if I want to find this area in between these 2 functions, because these functions swap places, notice here a function that is top and bottom is different from what is top and bottom in this piece. So when we do this, we're going to break this up into 2 pieces. We'll call this A. We'll call this B, we'll call this C. Our red area will be the integral from A to B. Look at what function is on top. The g of x function is on top, and the f of x function is on the bottom. And then we're gonna go, guys, I apologize, I didn't want to hold you very much longer, so I'm going to wrap this up super fast. Because these swap places, notice that the different function is on the top and a different function is on the bottom in each of these places. So if they swap places, you do have to split it up into 2 integrals. So when we come in next time, we're actually going to start with this one, which is going to be approaching area in multiple ways, and then we'll talk about cross sections.